NASA-funded telescope, the ATLAS Survey Telescope in Chile, first reported observations of the comet on July 1st, 2025 to the Minor Planet Center. And NASA has been tracking and studying Comet 3IATLAS ever since.
NASA just released new images of the rare comet 3IATLAS entering our solar system. And what those cameras captured has scientists talking. This object didn't grow up here. It arrived from somewhere far beyond our sun. And for the first time, multiple spacecraft were close enough to watch its approach in real time. The HiRISE come around the Mars Reconnaissance Orbiter that is 50 centimeters in diameter and therefore will allow us a pixel size of 30 kilometers. At first glance, it looked like a simple streak of light. But the closer the data got, the stranger the story became. What was hiding inside these new frames? And why did NASA move so quickly to share them with the world? Let's find out. The flash in the Martian sky. The first frame came in slightly grainy, the way fast-moving targets often look before the processing software settles. Inside the operations room for NASA's Mars Reconnaissance Orbiter program, no alarm sounded and no one jumped up from their desk. The team already knew an interstellar object named 3IATLAS was scheduled to pass near Mars in early October. They had spent weeks preparing tracking sequences, running exposure tests, and timing the HiRISE camera to the comet's predicted path. Still, waiting for a target to appear in a model is one thing. Seeing it arrive in real images is always something else. A soft glow emerged in the updated frame, a faint dot drifting across a starfield. One of the engineers leaned closer and said, "Looks like we caught it." Her tone held a mix of relief and curiosity, the kind that comes when the math finally lines up with the sky. More frames followed. The object's position shifted exactly where it was supposed to be, moving against the backdrop of distant stars as it crossed the edge of the HiRISE field of view. Even at this distance, there was something different about it. The dot was wrapped in a subtle haze, just bright enough to suggest activity. Someone zoomed in on the frame and murmured, "The coma is visible already. That's good." They began loading comparison frames. The staff knew they would not capture a crisp nucleus from this far out. But HiRISE's sharp optics still had the potential to show the comet more clearly than ground telescopes on Earth. It all depended on timing, exposure, and the angle between Mars, the spacecraft, and the comet itself. A second scientist typed in a new enhancement command. The screen refreshed, and the glow sharpened. The faint blur around the comet became more pronounced, a small halo of dust reflecting sunlight. "There it is," he said quietly, "exactly 19 million miles out." His voice carried a sense of achievement rather than surprise. They had expected to see something. They just did not know how well HiRISE would be able to catch it. Another engineer compared the latest frames with the predicted trajectory. Everything matched. The comet was right where the orbital forecasts said it should be, moving exactly as expected along its hyperbolic path. But seeing the object behave like a living thing, shedding dust as it approached the sun, added a weight that calculations alone never quite deliver. As more frames arrived, the mood in the room shifted. The glow strengthened. The dust halo looked more defined. The object felt less like a plotted point in a simulation, and more like a real visitor passing through space near Mars. Someone leaned back in her chair and said, "We have activity confirmation. This one is definitely awake." The room stayed calm but focused the way it always does when long preparation finally meets real data. They knew they were witnessing the first spacecraft images of an interstellar comet during its close pass by another planet. And although they did not yet know what the later photos would reveal, everyone understood that this was only the beginning. Tracing a visitor from deep space. By the time the Mars Reconnaissance Orbiter confirmed its target in early October, astronomers on Earth had already spent months watching the newcomer. The first hint came on July 1st when the ATLAS survey system in Chile flagged an object moving in a way that did not match normal solar system debris. At first glance, it looked like a typical faint comet, nothing dramatic or unusual in its brightness, but its motion told a different story. It was drifting across the sky just a touch too fast and on a path that refused to curve inward the way comets usually do. Someone at ATLAS noted that its orbit solution does not look bound to the sun. That line alone was enough to push interest into overdrive. Within days, the Minor Planet Center, NASA teams, and observatories around the world ran calculations. The numbers all pointed in the same direction. This thing was coming from outside the solar system. Its orbit was hyperbolic, a shape that does not close on itself. Instead of looping around the sun, it swoops in and continues straight back out into the dark. Astronomers call that the cosmic signature of a visitor that did not grow up here. The confirmation gave the object its name. It became 3IATLAS, the third officially recognized interstellar object in history, following 1 Oumuamua and 2 I Borisov. The rarity alone made scientists take it seriously. Interstellar comets are like messages that drift in from other star systems, carrying hints of the chemistry and environment where they formed. Some researchers compared them to bottles thrown into an ocean from another shore. The analogy stuck because it feels exactly right. You never know what clues might be preserved inside. As tracking continued through July and August, something else became clear. 3IATLAS was not on a casual pass. It was heading on a trajectory that would bring it close to Mars. That created a rare opportunity. Earth-based telescopes are powerful, but their view is limited by distance. Mars, on the other hand, has orbiters, spectrographs, and even rovers equipped with calibrated cameras. If everything went right, spacecraft around Mars could catch the object at a distance far closer than anything available from Earth. The challenge was timing. Comets move fast, and interstellar ones move even faster. Astronomers needed to estimate how bright it would be, how much dust it would release, and how its coma might change as it warmed in the sunlight. Some of these predictions were straightforward, drawn from typical comet behavior. Others were guesswork, because interstellar objects often refuse to act exactly like the ones born in our own system. A researcher at the SETI Institute summed it up neatly in an interview. "We know the physics, but every interstellar object comes with a personality." Throughout September, observatories refined the comet's trajectory. Each update confirmed that the Mars flyby would indeed happen with a closest distance of about 19 million miles. That is a comfortable distance for safety, but an ideal distance for observation. NASA teams prepared exposure sequences for HiRISE and MAVEN. The Perseverance rover team even ran night sky tests to see if its Mastcam-Z system might catch the comet from the Martian surface. All of this work built toward a single goal, collecting as much data as possible during the few days when 3IATLAS would pass close enough for imaging. Nobody expected a dramatic spectacle. They expected faint frames, useful measurements, maybe a hint of a tail. The aim was precision, not drama. But there was still one lingering question. Interstellar objects are unpredictable. Some brighten, some break apart, some release unusual gases. And with only 2 confirmed interstellar visitors in the past, nobody could say exactly how 3IATLAS would behave as it moved deeper into the solar system. Scientists kept watching. Each update tightened the orbit. Each calculation reinforced the same simple fact. A rare visitor was approaching, and within weeks, the first spacecraft images would arrive, carrying answers no telescope on Earth could have provided. The Mars advantage. If there is one place in the solar system perfectly positioned to observe a fast-moving interstellar comet, it is Mars. not because the planet itself offers anything magical, but because of what surrounds it. From above, Mars is circled by a fleet of spacecraft equipped with cameras, spectrometers, and sensors that watch the planet almost constantly. From below, 2 rovers sit on its surface with calibrated cameras designed to study fine details under the Martian sky. When scientists realized 3IATLAS would pass relatively close to Mars, they understood something rare was about to happen. The solar system had placed a front-row seat exactly where it needed to be. The Mars Reconnaissance Orbiter was the centerpiece of that plan. Its high-rise camera is one of the sharpest imagers ever sent to another world. Normally, HiRISE spends its time photographing slopes, boulders, ice layers, and dust patterns across the planet. Capturing a fast-moving comet from 18 or 19 million miles is not its usual job. But the team knew it stood the best chance of picking up detail that ground telescopes on Earth could never match. The trick was pointing HiRISE at the right spot at exactly the right time. Tracking a target like this is a bit like trying to photograph a speeding car from an airplane window while the aircraft is turning. Everything has to be planned down to the fraction of a second. While HiRISE handled precision imaging, the MAVEN orbiter prepared for something different. MAVEN carries an ultraviolet spectrograph that is sensitive to hydrogen emissions, a perfect tool for studying the volatile gases released as a comet warms. Water molecules in a comet do not stay intact for long. Sunlight breaks them apart, creating a thin cloud of hydrogen surrounding the comet. From Earth, this cloud is usually invisible. From Mars' orbit, MAVEN could see it. In September, scientists ran simulations to estimate how bright the hydrogen signal might be. The early numbers were uncertain, but even a faint detection would help reveal the comet's activity level. Far below in Jezero crater, the Perseverance rover team prepared for their own contribution. Mastcam-Z is not a telescope, but it can capture long-exposure images of the night sky if the timing is right. Scientists began running tests. They pointed the rover at known stars, took calibration frames, and checked how faint a target it could detect against a thin Martian atmosphere. Nobody expected the rover to capture a dramatic view of an interstellar comet from the surface of another planet. But if it managed to record even a small streak across the sky, it would be a scientific first. As October approached, the coordination between these missions became more important. Each spacecraft had its own challenges. HiRISE had to time exposures during a narrow observation window. MAVEN had to adjust for background ultraviolet noise from the planet below. Perseverance had to aim its cameras during the quiet hours of the Martian night. Every attempt carried risk. Any mistake in exposure timing or camera alignment could mean missing the comet entirely. The payoff, however, was worth the effort. Scientists knew they were about to gather data from an interstellar visitor at a distance that no Earth-based observatory could match. Observing from Mars offered something close to a sideways view of the comet as it slipped past the Sun. This perspective would help refine its trajectory, measure the shape of its dust coma, and study its outgassing patterns under different lighting angles. Even small differences in viewpoint could reveal details hidden from Earth. All that remained was to wait for the frames to arrive. The moment the images landed, the first files arrived quietly, without the drama you might expect for something this significant. A soft notification tone, a green indicator light, and a timestamp that marked the moment months of planning finally paid off. Across NASA's analysis rooms and remote workstations, researchers opened the new frames with a kind of controlled excitement, the same way archaeologists might lift the lid of a long-buried box. They already knew the object was 3IATLAS. They already knew it was a rare interstellar comet passing through our solar system. What they did not know was how well the cameras had performed or what secrets the new images might hold. For a few seconds, no one said anything. The high-rise frame loaded first, and the comet appeared exactly as predicted, but sharper than expected. A tight point of reflected sunlight sat at the center of a soft cloud of dust shaped by solar radiation into a faint arc. One of the analysts leaned back and said, "There it is. That is our visitor, clear as day." Her voice carried the satisfaction of a puzzle piece fitting into place. This was the first moment they realized how good the data truly was. The excitement grew when the MAVEN ultraviolet images opened. On these frames, the comet did not just glow. It was wrapped in a halo of hydrogen that made it look alive, as if it were breathing out a steady cloud of vapor as it passed Mars. The hydrogen emission was stronger and more defined than some had predicted. A member of the MAVEN team pointed at the display and said, "That is a clean signal. This is textbook hydrogen from water breakdown." The clarity of the image meant they could measure how the comet was losing mass and how sunlight was shaping its coma. Meanwhile, the stereo and SOHO images offered a completely different view. They showed the comet near the sun's glare, with wisps of tail structure fanning out across several frames. Some tails were bright, others faint, shifting with each filter and perspective. These images helped track how dust and gas responded to solar wind. This was the kind of multi-angle dataset scientists rarely get for interstellar objects, and now they had it captured from several missions at once. Only after the internal analysis began did NASA prepare its public release. And when they finally posted the full set of images, something unusual happened. Instead of presenting them as distant astronomy curiosities, NASA framed them as a unified story of a rare visitor entering our solar system. One scientist described it simply: NASA just released new images of the rare comet 3IATLAS entering our solar system, and these frames give us the clearest look we have ever had at an object born in another star system. It was not meant as hype. It was a summary of months of work and a dataset unlike anything previously gathered for an interstellar comet. The public saw the brightness of the dust coma. They saw the hydrogen glow. They saw the subtle curve of the tail. But for researchers, the real impact came from the details. The new photos revealed variations in the dust structure that hinted at the comet's rotation. They showed differences in gas release across different faces of the nucleus. They even helped refine the comet's hyperbolic path out of the solar system, reducing uncertainty by a large margin. These images were clues to how a comet formed under the light of another sun behaves when it crosses into our space. And for the first time, the world could watch that journey. Not from a telescope on Earth, but from spacecraft positioned throughout the solar system. What the images actually reveal. Once the excitement of the first release settled, the real work began. The images were beautiful, but beauty was not the point. Scientists needed to understand what these frames were saying about a comet that did not originate in our solar system. They moved from room to room, with digital models glowing across monitors, each one showing a different layer of information. It felt a little like taking apart a clock to see which gears were original and which ones had been shaped by a different watchmaker altogether. The high-rise images provided the most straightforward clues. At first glance, 3IATLAS looked like a bright core wrapped in a soft envelope of dust. But when researchers increased the contrast and measured the shape of the coma, they noticed subtle asymmetries. The dust plume was not perfectly even. On one side, the coma flared slightly farther out, which suggested that one face of the nucleus was shedding more material than the other. This uneven activity often hints at rotation. By studying the direction of the dust flow across several frames, analysts could begin estimating how the comet was turning as it traveled through space. It was too early for a full rotation period, but the hints were there. The MAVEN ultraviolet data added a completely different layer to the picture. hydrogen emissions can show how a comet reacts to sunlight. As water heats, it splits into hydrogen and oxygen, and that hydrogen drifts outward in a wide, diffuse cloud. In the MAVEN images, this hydrogen halo appeared stronger and more structured than expected. The fact that it showed such a clear signal from more than 18 million miles away meant the comet was actively shedding material at a steady pace. This comet is really cooking. The numbers backed him up. The emission rate suggested a level of activity surprisingly strong for an interstellar comet that had not spent long near the Sun. Then came the SOHO and stereo data, which opened an entirely different perspective. These instruments captured the comet closer to the Sun's glare, where dust tails can stretch into long shapes under the force of solar radiation. What they saw was a thin, bright tail shifting across multiple frames, paired with a faint secondary structure that shifted depending on the filter. These tail variations showed how different particles were being pushed by solar wind, almost like smoke moving through shifting breezes. Tracking these small differences helped scientists determine the size and composition of the dust grains. And in the case of 3IATLAS, the grains behaved slightly differently from those in many known solar system comets. Not better, not worse, simply different, as if shaped by a star that burns a little harder or a little softer than our Sun. When these data sets were combined, scientists realized something important. The dust patterns, the hydrogen envelope, and the level of activity all pointed to a visitor influenced by a different environment long before it entered our space. The data did not reveal the name of that star or the distance it traveled, but it showed that the comet carried its own story. The most practical outcome came from refining its path. With updated measurements from Mars orbit and solar observation missions, astronomers significantly improved the accuracy of 3IATLAS's trajectory. This allowed them to model how the comet will continue to move as it heads back toward the outer solar system and eventually into interstellar space again. For scientists, this chapter of the story was the most important one. The images gave them numbers, and the numbers gave them a chance to understand how an interstellar object behaves under our Sun. It was proof that even a brief pass through our solar system can reveal secrets carried from worlds far beyond our own. The visitor moves on. As the last of the data finished downloading and the analysis chart settled into place, a quiet understanding spread through the teams who had spent months following 3IATLAS. The comet had given them everything it could. New images, new measurements, new insights into how a traveler from another star behaves under the pole of our Sun. Now, it was already drifting away, moving along a path that would carry it back toward the outer edges of the solar system, and then into the deep black beyond. Astronomers tracked the updated orbit carefully. With the refined trajectory from the Mars flyby and the solar mission frames, they could follow the comet's movement with far greater precision than before. The improved numbers showed exactly how it would arc outward, passing beyond the reach of inner solar system instruments in the coming months. Eventually, it would grow too faint for any telescope to see, becoming just another point in the catalog of interstellar objects that slipped through our system for a brief moment and then vanished. But even as the comet faded, its importance grew clearer. The images from HiRISE, MAVEN, SOHO, and Stereo had done more than confirm its identity. They had shown what an interstellar comet looks like when caught from multiple angles under different kinds of light and at different distances. They had revealed details that Earth-based telescopes could never capture on their own. For scientists, this was not simply a record of a passing object. It was a template, a kind of instruction manual for understanding future visitors. There was also something quieter behind the data, something that several researchers mentioned in interviews. They spoke about how rare it is to watch an object that formed under another star react to the warmth of our Sun. They talked about the way the dust moved, the way the hydrogen halo expanded, the way the comet behaved like something familiar, yet subtly foreign. One scientist compared it to hearing an accent you can almost understand, but not quite. It was a reminder that the universe is full of worlds and histories we have never seen. By the time the final reports were drafted, one conclusion stood out. The comet had not stayed long, but it had left a trace. Its path was mapped, its activity measured, its composition hinted at through scattered clues in the images. And while it was already disappearing into the darkness, the information it carried remained behind, stored in servers, models, and the minds of the people who had waited months for this moment. In the end, 3IATLAS passed through the solar system like a visitor who never stopped to speak, yet still managed to leave a message. It came from distant light, swept past our sun, and continued on its way. What it revealed will stay with us much longer than the comet itself. What has impressed you the most about these images?